thank the organizers for the invitation. It's my pleasure to speak. So the title of my talk is Globally plus Regular Varieties. This is joint work with Bhargav Bhatt, Zalt Patakfavi, Carl Schweed, and Kevin Tucker, Joe Waldron, and Jakob Witasek. All right, so it's gonna take a while before we get here. So, but the main idea of this thing is to introduce analog of the globally F-regular varieties to mixed characteristic. And so, and to do that, let me begin by just recall you the definition of global F-regular in characteristic P. This is a recall. So for the moment, let me set X to be a Noetherian normal and F-finite scheme. Course of characteristic P. And I'm gonna let delta be an effective Q divisor on X. And so under this setup, so we say the pair X comma delta is globally F-regular if for any effective divisor on X, effective divisor, there exists some E bigger than 0 such that the map of sheaves from OX to FU lower star, OX twisted by P to the E minus 1 times delta round up plus D. So this this map of sheaves splits. Maybe I should say as the splits as map of OX modules. All right, so this definition is due to so this definition, like given here, is due to Carl Schweed and Karen Smith, but originally, like I guess if delta equal to 0, then this was originally introduced by Karen Smith. So let me, give you some examples of this globally F-regular varieties. So first, so let's say, so if you don't like pairs, let's just don't worry about this delta. Let's just work with X. So the definition is already very interesting when X is affine. So let's just look at that case. So if X is spec R and delta equal to 0. So in this case, this is something should be very familiar with the commutative algebraist. So X is globally F-regular. So this is the same as saying the ring is strongly F-regular in the sense of Huxon unities. So R is strongly F-regular. So this is in the sense of Huxon unity. So you should think about this globally F-regular as some like global analog of strongly F-regular rings, basically. Okay, so it's quite easy to see there's no delta, and this is just R. This is the R to the 1 over P twisted by some, just if you just think about D as a criteria divisor, this is just the map is just R to the 1 over P to the E, sending 1 to C to the 1 over P to the E, basically. Okay,
so just to remind me, so I'm thinking I'm confused now. Strongly F-regular, does that mean that every localization, every ideal is F tight closed?
No, that's
the diff.
That's yeah, okay. So let me just give you. So how about let me just write on the definition of strongly F-regular. So
Okay.
this means, you know, for every, let me just work with, I mean this setup, I'm just work with like say normal domain. So then for every C not equal to 0, oops, so let's just say inside R, there exists E bigger than 0 such that R2, I mean, I should write, okay, let me just write FU lower star of R, but this is really R1 or P to E, sending 1 to FE lower star C splits as R modules. Or if you don't like this, this is just, you know, this is just C to the 1 or P to E. All right, so this is the definition of strongly F-regular due to Hodgson-CUNY. And this condition, this implies, if you are more familiar with type closure, this condition implies every ideal is tightly closed. Although I'm not going to define type closure because I don't need it in this talk. Tightly closed. And in fact, this is equivalent to saying like every module is every submodule is tightly closed in any module, even if the module is not finally generated. And so, if you require that, then that's equivalent to strong F-regular. But if you only require it to be ideal, then that's, well, conjecture is the same, but we don't know. So it just, so this is stronger than saying every ideal is tightly closed.
Oh, okay, yeah, that's I remember that there was an implication, but I forgot.
Yeah, this is called weakly F-regular. Yeah, it's a good point.
So what's the
By the way, if you have questions, just feel free to just interrupt me at any time or type in the chat, or both are good with it.
So sorry, so what's the character 0 analog of this definition?
Yeah, I'll mention that. So this you should view this strongly F-regular as an characteristic P analog of KLT singularities. So,
Okay.
yeah. Let me just mark this as characteristic P analog of KLT. Yep. Let me give you some specific example out of these examples, right? So what are some strongly F-regular rings? For example, regular rings. Regular rings are always strongly F-regular. And so from this result, it's easy, well, it's not hard to show like direct summand of strongly F-regular rings are strongly F-regular. So in particular, if you have a direct summand of a regular ring, that's always going to be strongly F-regular. So that's not so hard to show. So basically, just because of this property, you can, because of this property and the fact that regular rings are strongly F-regular, you can write down many examples of strongly F-regular rings. For example, perhaps, maybe let me just point it out. So the rational double point of characteristic P bigger than 5 are strongly F-regular. Right, so basically, well, in characteristic, okay, imagine you're working characteristic 0. What you do is that you take a regular ring of dimension 2, and then you look at certain group actions and the invariant ring. So that's always, splits off from the regular ring. So that's the simplex or the ADE type singularities, whatever you call them. So those rings are direct summand of regular rings. Of course, in characteristic P, you need some mild assumptions because some pathologies might happen in the small characteristic, but if it's characteristic P bigger than 5, those rings are still direct summand of the regular ring. So you get that they are strongly F-regular, for example. Okay. Are there any more questions about this? And I believe for commutative algebraist, you can write down many examples of strongly F-regular rings. And there's actually a down-to-earth criterion for whether a ring is strongly F-regular. So this is the affine case. Affine case with no boundary. Okay. So this is just some well-studied object in commutative algebra. Okay, so let me also tell you some more global examples. So let's say X is a smooth projective variety. Let's say over K equals to K bar. This is, of course, this is characteristic P. And so in this case, I will be like, I won't be very precise here, but in this case, the pair X comma delta is globally F regular. So you should think about this as some sort of analog of log final varieties. Right, so what does that mean? That means basically minus Kx plus delta is ample. Okay, so okay, so what? So the more precise statement is the following. So this direction is actually precise if you have a pair such that X is a smooth projective over algebraic closed field. So then the pair is globally F regular under this definition. It satisfies this definition. Then you can show minus Kx plus delta is ample. So this is due to this is in the paper of Schreed and Smith. And the converse, this is the point that I'm going to be a little bit vague. So let me just say this holds when the characteristic is large, in large characteristic. So the more precise statement is that if you have a log final variety, let's say you start with something in characteristic 0, and then you do the multi reduction, and then you know, if you start with a log final variety and you do multi reduction, then for all p sufficiently large, the resulting pair is going to be globally F regular in this under this definition. And again, this is proved by Schreed and Smith in the paper that they introduced this globally F regular variety. Okay, and so this is so this thing is actually quite a restrictive assumption. So maybe let me just do an example out of this example. So let's say if the dimension of X equals to 1, again, let's just assume that there's no boundary. So then you see X is globally F regular, right? So basically, if you use this, basically what you want minus of the canonical class is ample, and that's very restrictive, right? So the only thing that can happen for a curve is that if the curve is P1. So, and that's basically, so this is if and only X is P. So if you have higher genus curve, they are never, projective curve, they are never globally F regular. Okay, so this is all I want to recall you about the global F regular varieties. Are there any questions?
I mean, this is true for any dimension?
Which one?
That the no, a global F regular implies.
So this is true, right? So
okay, I'm sorry.
This thing is true in every dimension, and I'm just going to give you an example in dimension 1, right? So that's yeah. And so the goal, as I said, the main goal of this talk is to just we wanted to find an analog of this globally F regular varieties beyond the characteristic P setting, because people used this thing to study higher dimensional birational geometry in characteristic P, and so now we want to study the birational geometry in mixed characteristics. So we want to introduce an analog of this in mixed characteristics. So clearly this definition does not extend, because this definition, you know, uses the Frobenius map, and in mixed characteristic we don't have the Frobenius map. So that's we have to introduce a variant. But before I do that, let me just tell you a theorem. So this theorem just sort of motivated us to introduce our new definition. This theorem is due to Oxler and CUNY. So again, I'm still working in characteristic P setup. So if R is an F finite normal domain, So suppose R is strongly F regular, then for any finite module finite extension, well, then we're going to say R2S splits as a map of R modules for any module finite extension S of R. Okay, so strongly F regular rings satisfy this property, turns out, and this is not very difficult to prove. And so, for example, right, so what are some strongly F regular rings? Right, so regular rings are strongly F regular. Well, that's the first case. So what is theorem? If you just combine these two things, it's just basically if you have a regular ring of character P, and you have a module finite extension, then the map must split as a map of R modules, and this is the famous direct-summand theorem. Of course, I'm just saying this in character P, so the proof is not so difficult. Okay. But I should also point it out that conjecturally the converse of this theorem is also true. So conjecturally, the converse also holds this in character P. Well, namely, right? So it is actually a big conjecture that so if you have a F finite normal domain, and suppose so this ring splits off from all its finite extension, then it is conjecture that R is strongly F regular. And this is still a wide open question in character P, but let me just point it out. So this is known when R is Q-Gorenstein. And that's a result due to anorexine. I guess originally in the Gorenstein case, this was due to Hawks and CUNY, and then Singh generalism to the Q-Gorenstein case. Oh, I mean, there are some more cases. This is known, but I don't want to go to technical details here. So, but you see that, I mean, I mentioned this theorem because remember our goal is to introduce a mixed characteristic analog of globally F regular varieties, and so in particular we want to generalize, or find an analog of strongly F regular rings to mixed characteristic, and then well, now this condition is sort of one natural candidate, because so this saying like the ring splits off from the finite extension, this does not depend on characteristic of the ring. So this makes sense in any characteristic. So this will be going to be one of this will be our candidate for the mixed characteristic analog of strongly F regular rings. And conjecturally, they should coincide with strongly F regular rings, but this is still part of a conjecture. But and so basically,
can I just quickly ask? Can you remind us, please? Remind me. The direct summand conjecture is that under the hypothesis that R is just regular,
right.
then this splits, right?
Yeah. So let me just put it here. So this is direct summand. This is a theorem now. So suppose R is regular, the theorem regular, then R2S splits for all finite extensions, module finite extensions. Of module finite extensions as of now. Okay, so what I'm saying is that so this theorem here plus the example 1 that I gave you already tells you like this is true in characteristic P. But of course, the hard case is the mixed characteristic case. I'm going to come to that later. I'm going to the direct sum and theorem. Are there any other questions? Okay, so if no questions, so from now I'm going to move on. I'm going to move beyond the. I'm going to move beyond the characteristic P setup. So let me just. Let me just tell you the setup that I'm going to work with for the rest of the talk. So X is going to be a Noetherian normal and integral scheme that is proper over spec R, where this R is a complete local domain. It's a complete local domain of, oops, let me just say. I want this is a complete local domain with residual characteristic P. So so the R could be equal characteristic P, or it could be mixed characteristic. So I want to work in this setup. And so, I mean, I mean, some of our definitions work without, I mean, it's in much more generality, but again, like I don't want to go to technical details. And also, because working in this setup, at least it, you know, I wanted to say, for example, it covers two main cases. So the first case is that, well, if you just don't care global things, right? So X could be spec R. So X is just a, you know, affine, like, you know, the spec of a complete local domain. So that's more like a commutative algebra setup. But it also covers the case, for example, you know, X could be, for example, X could be a projective over the p-adic integers. It could be a projective scheme over ZP, for example, right? So I mean, you could imagine like working in this setup, you know, we have some flexibility to, you know, move from the local case to the global case, all right? And of course, as usual, I'm going to set this delta to be an effective Q divisor on X. Okay, so this is the setup for the rest of the talk. So now let me give you the definition. So under the setup, we say the pair X comma delta is globally plus regular if for every F Y to X, which is finite and surjective, where Y is a normal and integral, we have, so the condition you want is that you want the map from OX to OY twisted by this round down of delta. This map splits as a map of OX modules. Okay, so this is the definition. Well, again, so first of all, for example, if you just assume X is affine, X is spec R, and let's say there's no boundary, X is spec R and there's no boundary. So what is this condition? This condition is precisely saying, well, what is a finite map of schemes? It just corresponds to a finite extension of rings, right? So in the affine case with no boundary, so this definition is precisely saying, you know, your R kind of splits off from all the module finite extensions. This is precisely this condition that I just said here. Okay, so this is in the affine and no boundary setting. Okay. And now,
so perhaps to link it a bit to the plus then, is it the same as saying that R splits off into its absolute integral closure?
Yes, yes, good point. Yeah, it's equivalent, right?
Yeah. Okay.
So, well, it's I shouldn't say it's equivalent in this setup because I'm assuming R is complete. So if you're not assuming R is complete, then splits out from all the finite extension is the same as saying the map from R to the absolute integral closure is pure, other than split, because I mean you don't know whether you can.
Oh, okay. Okay.
Kind of, yeah, but if you're assuming complete, everything is fine. Yeah.
Okay. Okay.
Yeah. And so again, let me just start with, well, I give you a definition, so I better give you some examples of globally plus regular or globally F regular pairs. So here are some examples. So first, I say in characteristic P. So that is, I mean, I'm assuming X or I mean, R has equal characteristic P. So then, well, if you think about this Hoxha-Huneke theorem, so it's just saying strongly F regular rings satisfy this condition. And so, well, so this thing globalized, right? So actually, so if X delta is globally F regular, then this pair is always globally plus regular. All right, so again, this is just the global version of Hoxha-Huneke's theorem. So it's not so hard to prove, right? And you know, conjecturally, at least in the local case, conjecturally the converse is also true. So that is the this thing that I wrote here in characteristic P. But we don't know that beyond the oops, sorry. Anyway, so I mean we know this in the Q-Bernstein case, but not in general. Okay, so now I really want to move on. So now let's say I'm not working characteristic P anymore. So let's just assuming this R has residual characteristic P, but the characteristics of R itself is 0. I mean the mixed characteristic setup. So now the question you might ask is that whether there are any examples like that. So and then so this direct summand theorem here that I wrote down here basically tells you like at least like in the affine case, regular local rings or like regular rings are always globally plus regular. So if R is regular, then this X equals spec R is globally plus regular. And this is just the direct summand. Another way of just saying the direct summand theorem. This is proved by Andre in 2016. So this already uses perfectoid method. So you see, even this statement is already kind of deep already in mixed characteristics. Okay, and let me just point it out. So from here, you can also get that if you have a direct summand of a regular ring, then it's globally plus regular. So you also get that direct summand of regular rings are globally plus regular. So for example, this rational double points of residue characteristic bigger than 5. Again, the rational, I mean, these are just, you know, I mean, there actually some work you have to do here because you have to show like this Gorenstein rational singularity of dimension 2. They when the residual characteristic bigger than 5, they are finite direct summands of they are direct summands of regular rings. And so again, like some pathologies might happen in small characteristic, so that's why we need this assumption. But once you know that they are direct summand of regular rings, then Andre's theorem basically tell you like they split out from all the finite extensions, so they are also globally plus regular. Okay, so let me I mean, so far all the examples I gave you it's just a no boundary case, like delta equal to 0. So let me also just mention a pair, really a pair case. So x equal to spec r and delta. Suppose I have a KLT surface or KLT pair such that this delta has standard coefficients. Right, so I mean this I just mean the coefficients in like belongs to the set 1 minus 1 over n. And the residue characteristic bigger than 5. And so then we can show that such pairs, so this is globally plus regular. All right, so so this is already not quite easy actually. Maybe I should say like in characteristic P, if your R, I mean, if your R has characteristic P, then this KLT surface are also globally F regular. So you can use, so in characteristic P, this is known before. So in characteristic P, so X delta as above are globally F regular. So this is known by, I think probably Hara or Hara Watanabe. They know this in characteristic P, and then we can prove this in the mixed characteristic. And so if I have some time, I will come back to this. Come back to this point, but I just want to show you like there are some pair version, and that's okay. Again, you have to avoid the small characteristic case because there are some pathologists that might have. Okay, any questions? Okay, so and now I want to show you. Let me show a first theorem that we can show. So let me call this theorem vanishing. So again, under the setup, so suppose the pair x comma delta is globally plus regular, and kx plus delta is Q cat here, and L is a line bundle such that L minus kx plus delta is big and semi-ample. So then what we get is that the HI XL is 0, wherever I bigger than 0. So this is, well, this should be viewed, I mean, especially if you're coming from a birational geometry background, so this should be viewed as the analog of the Kawamata V, or some version of Kawamata VWAG vanishing for globally plus regular varieties. And let me also mention that in characteristic P, and if this pair is globally F regular, so then this was proved. This theorem is due to Schreed and Smith, right? But their proof. So again, so we are again, as I said, I mean, we are largely motivated. We are largely motivated by the characteristic P results. So we have such result in characteristic P. So it's natural to, you know, if we introduce this definition, we want to prove that it satisfies the same analog properties as globally F regular varieties. But you know, necessarily there's going to be a different proof because their proof uses the Frobenius again. While here we need some we need to use a new we need to use a different approach because we don't have the Frobenius in mixed characteristic. Okay, and if I have time, I will come to say a few words on the proofs. Are there any questions? So this is the first theorem that I want to show you.
What is semi-ample? That's a weird.
Just some power is globally generated.
Oh.
So for example, it's stronger than it implies NF, so it's a slightly stronger notion than NF.
Oh, okay.
Actually, maybe let me just comment. So I think you asked since you also mentioned it. So the definition. So the globally whatever this I should underline this. So this globally plus regular. So we use this name. So this plus here, this denotes for the R plus, the absolute integral closure. So sort of our definition is really motivated from the R plus, even though like in the actual definition we want to keep anything like sort of in the theorem world, and so we use like for all finite cover, but it's really it's coming from the plus, the R plus, absolute integral closure. Okay, so next I want to introduce you let's see what I want to do. So okay, so I want to introduce the sheaf of stable sections, but in order to do that, so let me just tell you some like I'm just gonna show you one property of this globally globally plus regular varieties. So suppose I have this. Okay, let me say I have this pair. This is globally plus regular. And so if you think about it, okay, so oops, sorry. Okay, it's back. So right, so let me just so the definition is that I have OX to the push forward of OY, whatever this thing run down. This map splits as a map of OX modules. That means I can, for any finite surjective Y to X, I can find a map this way such that the composition is the identity. This is pretty much the definition. All right, so now I want to study this thing using Grothendieck duality. So let's see, if I apply harm to the dualizing complex, all right, so let's see what we get. So here I just get omega x dot. Well, of course I harm to this, so the arrow is gonna flip, right? So I have harm this to omega x maps to harm this one to omega x and harm this to omega x. So I have omega x here, and here I want to use duality for finite maps, right? So what I'm gonna get? I'm gonna get the push forward of omega y dot twisted by minus pullback of delta round down. Okay, I mean you can just ignore the delta if you like, but anyway I will just keep it. All right, so you can just you can just safely assume delta equal to 0 if you don't want it. Maps omega x. So here I'm using the duality for finite maps. So this is a map of complex of OX modules, and now I can take the first the first cohomology, because my dualizing complex are normalized such that the first non-vanishing cohomology is in degree minus d. So if I apply that, so what I get is that I get a canonical module or the canonical sheaf of X, and here I get push forward of the canonical sheaf of Y with this twist. And I get back to omega x. And now I could twist it.
Sorry,
Yep.
quickly, in the definition, was X smooth? I forgot now. Did we assume that
X is not smooth, X is just normal.
Oh, so why do your canonical module comes? How? I'm a bit confused where your canonical module comes from then.
This is not, this is just a dualizing complex.
Yeah, but then you associate with a canonical module, so all of a sudden your X is a canonical module.
Right, omega. So this is the canonical module. So this is the canonical sheaf, and this is the dualizing complex. The canonical module is the minus D's cohomology of the dualizing complex. I mean, it depends,
Okay. It's in the formally. Okay. Got it.
I mean, it depends on how you shift your dualizing complex. So
Yeah.
my convention, the dualizing complex is also like sits inside the the degree minus D, where D is the dimension of.
Sure. Okay.
Yeah. Sorry. Yeah. Please ask if you see suspicion.
So this omega X over the smooth locus, that's just the canonical bundle, right?
Yes, even though here I'm a little bit because I'm not working over a field, so I'm a little bit nervous about.
Oh, okay.
But if your X is defined over a field, let's say if X is normal, and then on the regular locus, this omega X is just the wedge end of the capital.
Using character T. Okay, I'm
Trivial differential.
using the character T.
So I think here really. So that's one advantage that I'm working in this setup, right? So the point is that you first pick a dualizing complex for R, and then how do I define the dualizing complex for X? You just use sort of okay. Let me just perhaps just do this side thing here. So let's say X to spec R, and this is a complete local ring. This has a dualizing complex. And now what I mean is that I just means the pi upper shriek of the dualizing complex of R. So that's going to be my definition of the dualizing complex of X. So yeah, if your R is a field, then that's just the usual. All right. So basically, I got this. Oops, sorry. So I have this. A map of sheaves on X, and now again the composition is just identity. And now if I twist it by this, I got so here I get back OX, and here I get okay. So here's a little bit work. So I have push forward OY, so KY. So that's basically omega Y. I mean I'm always assuming Y is normal. So and I have to minus this. And I also, since I'm twisting by here, so here I'm applying the projection formula. I also have to subtract the pullback of Kx. Right. Again, the composition is the identity. Okay. And so the reason I do that is that now, let me just continue this arrow. So now, since the composition is identity, I can take H naught. Right. So I still got a surge action. So I have H naught XOX. This is H naught Y, OY twisted by this crap. So KY minus round down of delta minus the pullback of KX. And now this H0 XOX. And since the composition is the identity map, in particular, what you get that this map is surjective. Right. So, okay, so let's just sum up. So what I show you here is that, so simply using this duality, so what you get is that if you have a globally plus regular varieties, and then for any finite extension, for any finite surjective morphism from Y to X, so this map induced by the trace map, this is always surjective with appropriate twist, as long as you twist it correctly. But this is induced by the trace map. So because it's induced from here to here, this is the trace map. So this map is always surjective. And so now, so this sort of motivates the definition of the stable sections that I want to show you. So basically, so now you can ask, like if I have an arbitrary kind of scheme X, so this image kind of sort of like measures how far my X is from being globally plus regular. And so now let me just introduce you the definition. This is the stable sections. So again, under the setup, so again, X is like a normal scheme, Noetherian scheme, proper over a spec of a complete local domain. So this is the setup. I have X delta, and L is a line bundle on X. You can just take X equal to, I mean, you can just take L equal to OX if you like. So now we introduce this thing B naught X delta L. We define this to be the intersection for all finite surjective maps with Y as normal and integral. I just look at the image of this map. So sort of the image H0Y OY twisted by KY plus the pullback of L minus KX plus delta. Sorry, it's kind of technical, but if you just take L equal to OX or whatever, this thing is precisely this twist that I did here. I mean, there's a swap in the round up, round down because I'm switching this minus to a plus here. Anyway, so this is something very elementary. I'm going to look at this H0 to H0XL. So we called it, so again, this is just you can see like this all sits inside here. All right, so let me just say where the intersection is taken inside H0XL, and this is a finitely, because remember our assumption is that X is proper over spec R, so this is a finitely generated R module. Right, so I'm just taking this infinite intersection, but I'm just taking this intersection as R module. Okay, so this is so basically this B naught, B0 is going to be a R submodule of H0XL. And as I already showed you here, so if you assume this capital X is globally, oh, let me just write here. So here's the remark. So first remark, I basically already show you this. If the pair is globally plus regular, so then since all these maps are surjective, let's just take L equal to OX. So all these maps are surjective, that means this B0 is just equal to H0. So that implies B0 X delta OX is just equal to H0 XOX. This is just coming from duality. And in fact, the other direction is also true. And this is not so difficult to prove either. Okay. And it's also not so hard to show. This is also equivalent to this B0 X delta L is equal to H0 XL for any line bundle. You see any L. Okay. So this I mean, people have been studied the character P. In character P, people have studied like very similar object before. So that's why we also the other reason we introduced this. And the second remark.
Yeah, I was wondering, what is the reason to call these stable sections? Is that?
Yes, you will see because,
okay.
Because it's yeah. So so suppose KX plus delta is Q card here. So then in the definition, in this definition, of B0, you can use the, here I'm just taking all the finite surjective morphisms, but you can also enlarge this. You can also take all the alterations, like generically finite map. For example, you can just take a birational map, projective birational map. So where Y2X, we can use this intersection where Y2X are all alterations, but the thing we can show is that you didn't get anything new. So it's the same. So basically, if you look at all the finite covers, so that already encode all the informations you get from birational maps or like even all alterations. So let me just gonna say B0 equals to B0 if you use alterations. Okay. And let me, so I understand there might be more some commutative algebras here, but let me just give you the local setup also. So if you just take X equal to spec R, let's say R, for simplicity, let me just say R is Gorenstein, right? So I mean, so this definition works in the general setup. So in particular, it just work in this local case. Let's say R is a complete Gorenstein local domain. And in this case, let me just take, there's no delta. Let's say L, you just take L equals to OX, which is R, and delta equal to 0. So in this setup, so I'm defining here, I'm defining B0 sort of spec R. And so here I put R here because this there's no delta and L is just this trivial line bundle. So I'm defining this B0 here. And this should be, okay, what it is, it's actually an R submodule of H0 spec R, but this is just R. So what I'm defining here in the local case, but this should just be some ideal inside R, right? So what's that ideal? It turns out, this requires a little bit work, but this is actually the image. Okay, if you look at the top local cohomology module of R, mapped to the top local cohomology of the absolute integral closure, you take the image from here, you take the image of this thing in here, and then you take the malice do. All right, so remember this image, since this HMD certainly surject onto this whatever this image is, right? So if you take the malice do, the do of the image is going to sit inside the do of HMDR. I'm assuming R is Gorenstein. So the malice do of HMDR is just R. So this is an ideal. So that's why this is an ideal of R. So, and that's coincide with the B0 I defined here, turns out. Okay, so this is the local picture. If you don't want to work with pairs or whatever. So this is
So what's the E
I
here?
only have like 3 minutes.
Sorry.
So let me just show you one result that we can do with the theorem, and perhaps I hope I will explain why this thing is important in the study of birational geometry in higher dimension. So let me just show you one theorem so that we proved.
Sorry, Linquan. So what's the E in the harm?
This is the injective hull of the residue field.
Okay, good. Thank you.
Yeah. So there's a well-known, like there's a malice duality functor in the, it induces an equivalence between finely generated modules and Artini modules. So you sort of move back and forth. All right, so I think I just have time to show you one theorem. So let me call this theorem lifting sections. So again, under the setup, let's say delta equals to S plus. So okay, delta is a Q divisor. I'm assuming it has an integral part and has a fractional part. I'm gonna assume the integral part is just a prime, actually a normal prime divisor, let's say for simplicity. So where S is a normal prime divisor, let's say Kx plus delta is Q cut here and L is a line bundle such that this L minus Kx plus delta again is big and semi-ample. Big and semi-ample. So then what we can show under this setup is that the image of B0 X delta, the fractional part of delta comma L contains B0 of S delta S L restricted to S. Let me just explain what do I mean by like image contains here, right? So I have, okay, so S is, oops, sorry. So this S is a prime divisor of X. So in particular, it's a subscheme, right? So we have a restriction map. So we have a restriction map from the global sections of L to the global section of L restricted to S. And so remember the sheaf of stable sections that I defined here, this B naught, whatever it is, this is a subsheet or like submodule of this, right? So here I have this B0 X delta L, it's a submodule of this. And inside here, remember X, so this little s is also a normal integral scheme proper over spec R, right? So the setup also works here. So here I also have a B naught. Delta, so delta restricted to S and L restricted to S. Okay? And so what I'm saying is that just if I look at this map, so then the image of this one inside here contains this guy. That's all what I'm claiming. So in particular, what you get out of this is that, so this is what I mean. So in particular, if the pair, the restricted pair S comma delta S is globally plus regular, so then you get a surge action, right? Remember, this first property that I show you here is that if you have a pair which is globally plus regular, then this B naught equals to H naught, and for every L. So if this restricted pair is globally plus regular, then this is equal. And so now what this theorem is saying is that, so this image of B0 already coincides with H0, so this map has to be surjective. So then HXL surject onto H naught as L restricted to S. Okay, so let me just take one more minute to explain why you might ask like why we care about this, why we try to prove results like this, and how does this conditions coming from. So this really coming from a Karamata Vivek vanishing characteristic 0. So for example, so note. So okay, so if I just write down the obvious long exact sequence, right? So I have H naught X comma L, so H naught S L restricted to S, right? So now what is the next term? The next term is going to be H1 X L minus S. All right. And so now if you just look at the definition, so what is this? What is L minus S? Well, S is sort of S is part of this delta. So if you do the right thing, so let me just tell you. So this is just H1X. So here I input KX plus the fractional part of delta plus this guy, which is whatever, something big and Simon ample plus something big and Simon ample. All right. And so now, so imagine you're working characteristic 0. If you're working characteristic 0, then at least if this, if you ignore this or if this fractional part of delta has simple normal crossing, then the Karamata Vivek vanishing tells you precisely that this H1 is 0. So this is going to be 0 if the Karamata Vivek vanishing holds. So of course, we are not working characteristic 0. We are working characteristic P or mixed characteristic. So there are some well-known examples that Karamata Vivek vanishing fails. But you see, the point is that what we did here is that we kind of work in a setup that you could pretend the Karamata Vivek vanishing holds, and that's why this theorem has applications to birational geometry in higher dimension. In the positive or mixed characteristic case, because you can sort of lifting sections from here to here under this extra hypothesis. Okay, so I think I would just, I'm already running out of time, so I think I will stop here. And yeah, sorry if yeah, if you have questions, please ask. Otherwise, that's it.
Thank you.
Thank you. Very nice.
Is there any question?
Yeah, I have a question. So, so this, so in like example 3, where you reduce to the local case, right?
Sorry, example 3, or so you mean this example?
I'm sorry. No. Much further down, like much more recently. Yeah, there.
Ah,
there. Yeah. So, so you were saying like this B0 thing will be some ideal, right?
Yeah, in this case.
Yeah, so I wonder, I mean, like this is completely naive and it's probably wrong, but I wonder, given the way that this thing is constructed, right, is by taking all these like finite morphisms onto X or something like this, could it be like, so there's this thing called the, I wonder if this is like some type of like conductor ideal or something like this. Does that make any sense? Do you know what a
I know, but well, not quite, because we are assuming everything is normal here. So
okay, so it's not
yeah,
like
I was thinking about conductor as sort of a measure of how far you think from being normal, right?
okay, yeah, never mind. Everything is normal.
Yeah.
This is kind of stupid. Yeah. So I guess like, yeah, I don't know. Like it's some type of ideal that's measuring what though? Then maybe like, is there some more conceptual idea of what the ideal is?
The more, I mean, I will say the moral is, I mean, if you, especially if you're coming from a computer algebra background, so then it's more or less like, so this thing is, I mean, or here is a measure of how far like sort of this axis from being kind of splits off from all the finite extensions, right? Because, okay, if R splits off from all the finite extensions, as I said, then R to R plus is pure. Actually splits because R is complete in this case. But if R to R plus is split, right? So then what is this image? Oops, sorry. Right? So this image is just the whole thing. So if you dualize, then that's really R. So in general, of course, it's not going to be R, it's going to be some ideal. So you could imagine that ideals measures how far your ring is from being a plus regular ring, or like a splinter, if you know what splinter means. It's not like it's just like, I would say it's just measure, locally, it's just like measure how far R is from being, having this property, like splits off from all the finite.
Yeah, which makes sense, I guess, because that's kind of how you're defining it. Like you want it to do this in some sense.
Yeah, under the Gorenstein hypothesis, I should say. Without the Gorenstein, it's actually you actually need to do with the omega or something like that. But yeah, in the Gorenstein case, I'm just simplifying this. I mean, in the Gorenstein case, it measures how far R is from. That.
So yeah, perhaps going on the same question then, because I got also a little bit. It seemed that it's very canonical defined, but on the other hand, what if that ideal is principal? Can you renormalize whatever to make it?
Actually, it's. I think in this setup, it's probably never going to be principal, because we assume. Okay, so this is something that we cannot quite prove yet. Well, but we probably have some. But I can probably show it's never. The point is that, okay, so we expect at least this thing like behaves well under localization, right? So, but remember all our stuff.
Oh, okay.
So if you localize at height 1 prime is already regular, and of course regular rings are, satisfied. I mean, regular rings are globally plus regular. So so if you localize at height 1 prime, I expect that they are just all they're just the whole ring. So this ideal has height at least 2, and that's true in characteristic P, because in characteristic P we know that this thing localizes. In characteristic, it's not so clear. we have some partial results towards localization, which probably show is never going to be principal, but we don't have full localization actually.
Okay, so if potentially it is the case that this can only have height 1 if it's actually the unit ideal, something or
yeah.
I not say it right,
I
but
was,
yeah.
right. That's right.
Yeah,
That's right. Yeah, I would say that.
Yeah, so perhaps can you also say something, I mean, unless perhaps that's, a bit, what kind of, do you use some type of plus techniques and also these perfectoids in improving your first theorem, the vanishing theorem?
Yeah, I mean, I don't have time to discuss this, but if you like, so let me just, okay, if I can take like 3 minutes, 5 minutes, so then let me just tell you the main ingredients we use in proving this stuff.
Okay.
The main ingredients of the proof is the theorem of Bargov-Bott. Right, so he showed, again, let me just say under the setup, I mean, this X delta is proper over a complete local domain. If the L is big and semi-ample, then what he showed is that, okay, let me just write it. This is going to be Hj of R gamma M and R gamma X plus the pullback of L inverse, it's 0 for any j less than the dimension of x. Okay, where pi from x plus to x, this is the absolute integral closure.
Oh, okay.
Okay, so let me just for example, I mean, I think people like the, I mean, also for me, I like the affine case. So let's say x equals to spec r. So what is this, right? So if x equals to spec r, and I take L equals to OX, I mean, in the affine local case, there's no interesting line bundles, it's just OX, right? So then what is this theorem saying? So this theorem is saying precisely, right? So, okay, so if x is affine, so there's R gamma doesn't do a thing because everything is going to be affine. So, so this is just, you pull back OX to OX plus, you just pull back R to R plus. So this is just R plus. So what this theorem saying is really just saying all the lower local cohomology module of R plus for every j less than the dimension of R. So you could think about this, thing here is kind of like a relative version. Oh, by the way, I shouldn't say this. So this thing here. So in positive characteristic.
Yeah, then we know this, right?
Yeah, this was proved by Hoxer-CUNY.
Yeah.
And so basically what Bargov did here is that, so first of all, he generalized Hoxer-CUNY's result from characteristic P to mixed characteristic. That's like one big result. And also, actually I shouldn't say, he also did a relative version. I mean, the relative version is actually more work. It's actually, it's not like the relative versions just follow from the absolute case. You have to do more work here. So basically he did two things. So first of all, he generalized Hoxer-CUNY to mixed characteristic, and then he proved this relative version. And so this is the main ingredient we used.
And how did Bott prove that? What did he use there? This is also perfectoid theory or something?
Yeah, this is the point that he uses the well, not only perfectoid. He uses some of his work with Luray on the p-adic Riemann-Hilbert correspondence, and then he also used this prismatic cohomology that he developed with Scholze.
Oh.
So this is, I mean, I will say like so from here. So from this theorem to our result on the vanishing and this lifting section, these are like, I wouldn't call them easy, but it's not too bad. So the deep thing is happening here.
Yeah, because that's I mean, I didn't even realize that this result was true in mixed characteristic. Oh yeah.
Right. So I mean, at some point, I think this result is like too optimistic that people never even conjectured this. People.
Right. Yeah.
Even some people conjecture this is false, but somehow he managed to
Wow.
prove this thing.
Yeah, I'm quite surprised by this result. Wow. Okay, thank you. Thank you. It was very nice.
Yeah, so Linquan, one more question from me. I don't know if there's other questions. So in the definition of the plus regular, can you just I mean, is it enough just require F to be alteration instead of all finite surjective morphism?
Yes, you can. Yeah, you can also say for
Only for alterations, right?
okay, you have to be careful, right?
Uh-huh.
So the condition says all finite surjective maps. You can also say all alterations as long as, let's say this. I mean, but for alterations, there's first problem is that you have to well define this pullback of delta. But okay, let's say delta is QCAT here, right? So then it's the same. I mean, so then saying this definition for all finite surjective maps is the same. It turns it's not obvious, but it's not obvious. But we can show this is the same as saying for all alterations or regular alterations, the map splits. But you have to be a little bit careful because it is not enough to check one alteration. We actually have counterexamples. So this is basically because of this. You look at here. So so basically, so saying this thing is globally plus regular, it's just saying B naught equals to H naught. And but B naught is the same regardless of whether you use finite maps or alterations, as long as your advisor is QCAT here. So it's like so if you use the definition, so if you use all alterations, you didn't get anything new. So so you can say the same thing true for alterations, but I guess so this is like this is like why basically mixed characteristic is harder than, because in characteristic P, there are some results, I guess, proved by Schreed, Tucker, and Manuel Brickley that, so I look at the infinite intersection here, but it's actually enough to look at one alteration in P. But this is no longer true in mixed characteristic. You really need an infinite intersection.
I see.
So this is like one difficulty in studying this thing.
Great, thank you. So any other question?
Can I just ask a quick question? So I'm not a commutative algebraist, but and what I'm asking is only tangentially maybe related. So you mentioned the direct summing conjecture, which, by the way, I think it was only proved quite recently. Right, here, so like a few 2 years, 3 years ago or something, maybe 4, the preprint.
Yeah, I mean, proved 5 years ago and it's published in 2018. Yeah.
Oh, I see, 2018. 16. Okay, yeah. And so there's this other conjecture called I think strong direct summing conjecture, if I remember correctly. But that's right. So that's something about complete local rings, but it has to do also with ideals. And I'm just wondering if you know, is that actually
that all true now? Is all the homological, all those things? Well, I shouldn't say all, but yeah, but the strong direct summing you are asking is proof. It's okay. It's proof.
So is that also proof? Because I mean, the way I remember it is not. So it's not obvious to me that it's stronger than I mean, in principle.
It is stronger, but it's proved. Okay, so let me just so the strong direct summing. I mean, I hope you know the statement or whatever. You can Google this.
Yeah. So it's something about if you have just like that, an extension of complete local regular rings, and what is it? I think you take an ideal, a prime ideal in the bigger ring that sits over.
Okay, so the statement is that if you have R to S such that this thing is
maybe there's a equivalence.
And this is a whatever complete local domain, and you take a height 1 prime such that the height 1 prime contract to the part of a regular system of parameters, and then I guess this is saying basically this one something like that, X to P splits.
Yeah. Okay.
X module, something like that. I might forget. I mean, yeah. But this is all true because if you, well, I guess I should say so. So in this case, this was first proved by Ray Heidman himself. we basically adapted Andre's proof of the direct summon theorem. We proved this version, but then immediately after our work, so Andre proved the existence of weakly functorial big Macaulay algebras, and in that, and you probably know like all these homological conjectures follows from the existence of weakly functorial big Macaulay algebra. So what does that say? Basically, you have a weakly functorial BCM. So what is that saying? That's basically saying if you have a map of complete local domains, right? And then you can fill in this diagram with a you can find a big Macaulay R algebra B and a big Macaulay S algebra C such that this diagram commutes. And this is what they call the weakly functorial big Macaulay algebras. It turns out the strong, for example, the strong direct summon thing you ask, it follows. Not too difficult. People realize it's like a long time ago. It follows from more, but now, so let me just also point it out. So this theorem of Bargov or Bat, right? So so Andre proved, so this is due to Andre, right? Andre said this is a weakly functorial B Macaulay algebras, but he didn't construct explicitly what is B and what is C. And now with this Bargov's result, you can just use the R plus and S plus in equal and mixed characteristic. So in equal and mixed characteristic, you can just, let's say this is a map of complete local domains. Then what Bargov showed is that this one works. This is a weakly functorial big Macaulay algebra. I mean, if you're willing to take completion, whatever, right? So this is a weakly functorial. Right, so everything basically follows. I mean, ultimately everything follows from this. But you know, this is quite recent. This is, I'm interested. This is like last year.
Oh, okay. This is very recent. Yes.
Yeah,
yes.
very recent.
So you said this covers also these conjecture about the existence of big calling modules.
Yeah, because well, what Bat's result basically shows this one is a big Macaulay algebra. But
Algebras, yeah.
Existence of big Macaulay algebra is due to Andre. But Andre didn't show this one particular one is, but Bat proved that this one is big Macaulay algebra.
Is there like recent either reference preprint where at least you know, not the proofs, but at least the status of all these are somehow mapped out a little bit for, you know, the non sort of the, you know, outsider who, you know, I know about these conjectures, but I'm not a specialist, so I'm kind of just curious too.
Yeah, unfortunately, I don't. I mean, of course, you can check all their original papers, but so if you want to get a quick survey, for example, you can look at Andre's ICM report. This is in 2000. Of course, I mean, he didn't cover this because I mean, this is like last year. I don't.
Yes, right.
Yeah, but
maybe even there. So maybe even the, you know, these papers could have in their introduction something about this.
Yeah, probably. Yeah, well, I won't mind just looking at his papers. This one's introduction. Maybe
Yeah.
surveys something. You can also just Google one of Bargov Bat's talks, and he surveys at some point. But I don't.
Yeah. Okay. Yeah, it's very interesting. Yeah, quite amazing, all these conjectures. Yeah. Thank you. Very interesting talk. Very nice talk.
Yeah, thank you.
Thank you. Very interesting. Yes. Yeah.